Yeah, we do a lot for both combustion engines and battery systems. Again, on the battery system side, the thing that's really kind of the hot topic here, no pun intended, is battery safety, right? So you see a lot of talk about thermal runaway and how that can potentially lead to a battery fire. People sometimes forget hybrids have internal combustion engines, right? And electric motors. And I think that for a lot of people, that's probably the best option right now because you can get around, if you have a plug-in hybrid, you can zip around the city on a small battery, but if you need to make that long journey every once in a while, you're doing it with an engine, you're not relying on this really massive battery pack to do that, which in itself is not very sustainable.
Talk to me about the uphill battle of convincing people to use autonomous meshes, especially in the industry, like where they're resistant.
I think Henry Ford really said this. You can fact check me on this, but he said something like, if we would have asked them what they wanted, they would have said faster horses.
Ladies and gentlemen, Kelly, finally, you're on the show. Thank you so much.
Thank you for having me. I'm thrilled to be here.
Yeah. Already butchered your name in the beginning, so that's a good start into the podcast. Today, I want to talk about CFD, Autonomous Meshes, Convergent Science, the company that you've built over the last years, and potentially combustion engines versus EVs. But before we jump into that, can you give us a quick introduction? Who are you in the first place, and what have you been working on over the last years?
Sure. My name is Kelly Senecal. I'm one of the co-founders of Convergent Science. We are a computational fluid dynamics software company. We create and sell the Converge CFD software package. We work in a lot of different areas. We're probably most known for our reacting flow simulations. That's kind of where we started and kind of where we grew up. But we've been expanding into lots of different areas like biomedical, wind turbine CFD, you name it. And so yeah, that's who I am. I wear a couple of different hats. I'm also a visiting professor at the University of Oxford, and as you know, I do a lot of advocating for technology neutrality in transportation. The whole ICE versus EVs debate. I believe we need both, and so yeah. But my main job, my day job, and what I put most of my time into is Convergent Science.
Excellent. And you forgot to say that you're also an excellent TED speaker, a TEDx speaker, I should say.
Oh, that seems like so long ago now, but
It
thank
was
you very
like
much.
7 years ago, I think it was.
7, 8 years ago, yeah.
7, 8 years. Yeah, I have it actually open. I watched it before the podcast. The title is In Defense of Internal Combustion, where obviously some people in the comments were extremely triggered by what you said. But to me,
Yeah.
at least it made a lot of sense. Maybe we jump into that before we talk about CFD and kind of how you
Sure.
found love for simulation. Why combustion engines and why not only EVs?
Yeah, that's a really good question. And when I did that TEDx talk, it was an interesting time because it was right before, it was late 2016 when I actually did the talk. The video came out, I think, in early 2017.
Mhm.
But 2017 is the year, I call it the year combustion died. And of course, I say that sarcastically. But that was when, I don't know if you remember, but it was a while ago, but there were tons of headlines. Every day I'd come to work, open up my web browser, so-and-so says engines are dead, whether it was a car company or a government, declaring bans on internal combustion engines. And so I kind of hit that, maybe luckily, I did that TEDx talk kind of at the right time. It was right before all of that. And I really think, I think EVs are a great technology. And my company, you can see behind me, there's a battery on the wall behind me, a battery simulation. We do a lot of thermal runaway simulations for battery safety. I think it's a great technology, and I think for a lot of people, it is the best solution out there, even now. But I think, we're a diverse world, and, what's good for someone in one city is maybe not good for someone who lives on a farm or lives in, a rural area or something like that. Income levels, whether you own your own home or not for charging, infrastructure. There's just a lot of things that are still, it's still not for everybody, EVs. And so I think the combustion engines have a long runway. Whether it's a standalone internal combustion engine, hopefully with more and more renewable fuels being used instead of fossil fuels, or even a hybrid. Hybrids, people sometimes forget, hybrids have internal combustion engines, right? And electric motors. And I think that for a lot of people, that's probably the best option right now because you can get around. If you have a plug-in hybrid, you can zip around the city on a small battery, but if you need to make that long journey every once in a while, you're doing it with an engine. You're not relying on this really massive battery pack to do that, which in itself is not very sustainable. So yeah, I think there's quite a future for internal combustion engines in a lot of applications in a lot of locations around the world. And I think we need to kind of get over this one versus the other, and they really need to work together. And I think that's the most sustainable way to move forward.
Yeah, that makes sense. I'm wondering what are some of the most or the biggest misconceptions you hear maybe or even read under your LinkedIn post when it comes to combustion engines?
Yeah, one misconception is, we talk about reducing pollution in city centers, and EVs are great for that. So they don't have a tailpipe, right? But a misconception is that, the emissions coming out of an IC engine, a modern IC engine, are still extreme. And to be fair, we've come a long way with reducing the emissions coming out of internal combustion engines because of the engine itself, but also because of the aftertreatment systems, right? We have little chemical laboratories sitting on inside the car to kind of take care of those emissions before they come out the tailpipe. They're still not zero, and if you know me, I hate the phrase zero emissions. I think nothing is zero emissions, but they're extremely low. Cold start is still where most of the emissions come from, and that's still an issue. We're working on that, but it's not as if emissions are just gushing out of the tailpipes of these modern IC engines. We've effectively, this is a bit controversial, but we've effectively solved the criteria pollutants problem from internal combustion engines, from internal combustion engine vehicles. What we haven't solved yet, though, is the CO2 problem. And so that's when things like renewable fuels come into play.
Mhm. If we hypothetically would be able to compare EVs and combustion engines in terms of CO2 emissions, like can we even compare that, or like how do they compare with each other?
Yeah, that's a really good question, and there's a lot of a lot of debate on that. A lot of our regulations in the U.S. at least are based on the tailpipe alone, right? So if you're comparing the CO2 emissions from a regulation standpoint, you get zero for the EV. There's no tailpipe, and you
Hmm.
get whatever it is for the IC engine vehicle. That's not correct, right? Because we've just moved the fuel kind of away from the vehicle, right? So we're burning fuel in a power plant, or hopefully we're using more and more renewable energy to create the electricity. But in most of the world, we're still using a significant amount of fossil fuels to create that electricity. So you have to do something called a life cycle analysis in order to do a fair comparison, where you draw your control volume not just around the vehicle, but around the whole system, right? And the whole system would include producing the batteries, producing the vehicles, whether it's an IC engine vehicle or an EV, how you get the energy to the vehicle, the electricity production, all of that. And once you do that, you start to see that number one, EVs are not zero emissions, and number two, they're not as different as you might expect in terms of the emissions, especially if you're looking at something like a full hybrid electric vehicle, the kind you don't have to plug in. So as a consumer, you're not changing any habits, right? The difference between the CO2 levels from a full hybrid and a fully electric vehicle in a lot of places in the world are not so different. And in fact, sometimes the full hybrid actually beats the battery electric vehicle. Depends on where you are. Other places, the battery electric vehicle wins on CO2. But the point is, they're not that different.
I see. So what can we do in terms of simulation to maybe investigate or maybe optimize combustion engines and maybe battery systems? What do you do at Convergent Science?
Yeah, we do a lot for both combustion engines and battery systems. Again, on the battery system side, the thing that's really kind of the hot topic here, no pun intended, is battery safety, right? So you see a lot of talk about thermal runaway and
Mhm.
how that can potentially lead to a battery fire. And I'm not an alarmist where I say, all the EVs are blowing up or whatever. It's fairly rare, right? But at the same time, you don't want it to happen ever, right? Because if it happens once, that's too much. And so we do a lot of work, even the simulation behind me, it was part of a thermal runaway problem where you can use the CFD to say, okay, if we get ignition in this one location because of a nail puncturing the cell or something like that, does that propagate and does that effectively turn into something like thermal runaway, which could cause a fire? So we do a lot of those simulations to help with battery safety. And then we also do electric motor simulations, cooling electric motors. That's a big problem that people have right now, and CFD can really help with that. Um, on the combustion engine side, we do everything. We do a lot of the work right now is looking at alternative fuels, right? So hydrogen is a really hot topic in the internal combustion engine space. Other fuels like ammonia, I never would have thought we'd be talking about ammonia as a potential fuel, but we are. It's zero carbon, right? It's NH3. So while it has its own issues, for sure, it is zero carbon. Other fuels like biofuels, e-fuels, methanol, made synthetically and things like that. So a lot of the work that we're doing today is looking at these alternative fuels and can we get similar types of performance or maybe even better performance out of the engine using these renewable fuels or alternative fuels.
How did you first get started with simulation? Like maybe talking about your undergrad years. Why have you been so fascinated by simulation in the first place, and then later on combustion, CFD,
Yeah.
autonomous meshes, etc.?
Yeah, it's a great question. Kind of just happened by chance, sort of. I was a physics undergrad, physics major. Was doing research between my junior and senior year at the university with Professor Cook. He was my advisor. And I was working on finite element analysis. And I was doing some stuff by hand. I was writing some pretty simple code and solving some problems. And it was kind of fun. That's when I started really getting into coding and things like that. And my professor walked into the physics lab one day and he was holding I think it was a CD. It said FIDAP on it. He's like, have you heard of something called CFD? I was like, no, I have no idea what you're talking about. And so he said, Computational Fluid Dynamics. This is how old I am, by the way. He said, Computational Fluid Dynamics. Let's install this on this SGI machine. We had this brand new SGI machine. We were so proud of it. We put it, I think it was an SGI. Yeah, it must have been. And so we put FIDAP on there, and it was basically finite element solver for CFD, right? It was solving the Navier-Stokes equations using finite element analysis.
Mm-hmm.
And I was just blown away. I was fascinated, right? That I could solve these problems that I was trying to do by hand and much, much harder problems, on the computer. And then just seeing visually, like, the first contour plot coming back, it's like, wow, that's amazing. And at the time, I had never seen that before, right? And so it was really amazing to me. And I said, that's what I want to do. That's what I want to do. How do I do that? And he said, well, we don't do a lot of that in the physics world, actually, in grad school, but engineering and applied math, that tends to be where the CFD mainly gets done. So I said, okay, I'm applying to engineering for graduate school. I applied to a bunch of different schools, and depending on where I ended up going, it would have been a completely different application, right? It would have been aerospace or biomedical or whatever. And the first person that got back to me was Professor Rolf Rates from the University of Wisconsin-Madison. He called me up and said, we want you to come here and work on engine CFD. I said, engines? I don't really know much about engines. I really didn't at that time. I tell people, like, I hug engines all the time, but like I did not grow up an engine guy, right? I wasn't like fiddling in the garage with my dad or something, fixing engines. I didn't touch it, right? I said, that sounds interesting because it's such a complex problem, right? It's highly turbulent. There's phase change. There's chemical reactions. There's moving geometries, moving boundaries, valves and pistons. So it's not just a simple CFD problem. It's one of the hardest problems you could do. So I thought, okay, that sounds like a challenge. I want to go do that. And so I did that, and that's sort of where my love for CFD grew, but also my love for engines and combustion. And I sort of really gained an appreciation for how important that is to our society, but also how much work we need to do to clean it up, right? And so that's really where my love for engine CFD started.
Mm-hmm. Was it also when the idea of autonomous meshes was born because of the moving parts in a combustion engine? Have you developed that from scratch, or was there already existing code that you just leveraged?
No, we developed Converge from scratch, and actually Converge was initially called Moses. I don't know if you know this. Some people know, but not everyone. It was going to be an open source code. And so Moses stood for, there are a couple different acronyms that are out there, but modular, that's the other one. Modular open source engine simulation. That's what Moses stood for. That's what the letter stood for. And we thought we were going to have this be an open source code, and it was going to essentially replace a code called Kiva. And Kiva is what we used in grad school to do our engine simulations. And at the time, it was a great code. I mean, the guys that wrote that code were brilliant. But it was a serial code. It was time to kind of move on from Kiva. So we had this idea, and yeah, we wrote Moses, which turned into Converge, entirely from scratch, with the idea that we were tired of making meshes, right? Because in Kiva, it's block structured, and now think about having valves moving up and down and stuff like that. It was very picky about the grid, and it would take us sometimes weeks to make a grid, and we had some of the best tools to do it. we actually wrote a tool called G-Smooth. Uh, my partners and I, actually Keith Richards, who's one of my partners, it was really his brainchild. He wrote a code called G-Smooth, which made Kiva meshes really quickly. But really quickly, I still mean days, maybe even up to a couple of weeks, right? So we were like, we wanted to start a consulting company in Madison after graduate school. We started it actually while we were in graduate school, but we wanted to kind of do it full time. And we thought, what can we do? Well, we'll do consulting with Kiva initially because we're really good at that, and we can help all of the engine manufacturers and automakers. And then we thought, do we want to spend the rest of our careers making meshes, or do we want to actually do the engineering? We were sick of making meshes, so we thought, well, what do we do? Well, let's write a new code. We were naive enough to think we could not only start our own company, but write a brand new CFD code and anybody would care, right? And it turns out people cared. So the idea of autonomous meshing really came out of just being tired of making meshes. And yeah, it was back in around 2001, 2002 when we kind of started down that path.
That's super interesting. Talk to me about the uphill battle of convincing people to use autonomous meshes, especially in the industry. Like, were they resistant? Like, how did they perceive this concept of an autonomous mesh?
Yeah, that's a really good story, or a really good question. Here's how it would typically go. We'd go into a company, and usually like the manager would be there, and maybe a few people on the manager's team, the engineers that were actually doing the CFD or whatever. We'd go in and we tell them what we had, and the first response from the manager was, "Oh, we already have that figured out. We already know how to make meshes quickly. It's not a big deal." The manager would then ultimately leave the room, and the engineers would say, "We don't know what he was talking about. And making meshes sucks. Like we hate it, and it takes forever, and like this and that." Nobody wants to say that their process isn't good, right? Yeah. But the engineers that were actually doing the work, they were telling us the truth. So then we're like, aha, okay, so we're onto something here. And then we would say, we have this autonomous meshing, and it makes the grid for you automatically at runtime. All you're doing is inputting a couple numbers, like what's my base mesh size going to be? And do I want to turn on AMR or not, and things like that. So you input a few numbers in an input file or in the UI, and it makes it for you at runtime. Nobody believed us at the time, right? They said, oh, well, if first of all, that's going to take forever to crank out that mesh, especially if you're redoing the mesh every time step like we do, right? So we redo the mesh every time step. So as the flow evolves, so does the mesh, right, through AMR. And so they didn't believe that it could be done really quickly. And to be honest, it wasn't quick when we first did it. It took hours. And our real breakthrough was making that process basically instant. I mean, you don't feel it as a user, right? That was one of our big breakthroughs. And so they didn't really believe it, but they also thought, oh, you're making it automatically. You must be cutting corners. You must be simplifying the geometry. You must be doing this or that. We're like, well, how can we convince you? And so what we do is we'd show up at their office and we'd say, bring us your hardest geometry on a thumb drive or whatever. We haven't seen it before. We've never seen it. And we'll have this running for you in like 10 minutes. 5 minutes, 10 minutes. And the reason why it was 5 or 10 minutes is because you had to like flag the boundaries and say inflow, outflow, that kind of stuff, right? Stuff that you always have to do in CFD. And so once we started running their case in front of them that quickly, that's when people were like, okay, wow, this seems real. So that's how we started convincing people.
Really cool. What did you learn from as an entrepreneur building Convergent Science, especially dealing with clients that are very skeptical?
Yeah, well, I've learned a lot. Yeah, you have to be careful with customers because on the one hand, our customers are part of why we're where we are today, right? Because customer feedback is gold, right? Like if a customer says, I really need this for my workflow or this feature, chances are not only they're going to need it, but all of their competitors are also going to want or need that. So customers really help drive the direction of our software. Mm-hmm. But at the same time, customers were not asking for autonomous meshing. Of course, people would always wanted faster meshing, but it wasn't like a customer was saying, hey, can you go put autonomous meshing? No, they didn't have that idea, right? And so we had to, and I make this analogy with Henry Ford, right? Henry Ford had this, I think Henry Ford really said this. You can fact check me on this, but he said something like, if we would have asked them what they wanted, they would have said faster horses, right?
Correct. Yeah.
And that's what the customers were saying is we want faster mesh generation. We want faster turnaround. We want better chemistry. We want all of this. And that's great, and we need to give them that. But at the same time, we turned around and gave them an automobile, right, through autonomous meshing. We didn't just make the meshing faster. We completely turned it on its head and said, the solver is now going to make the mesh for you intelligently from learning from the flow, essentially. And so, yeah. So balancing customer feedback along with, we think we have something you want, you may not know you want it yet. Balancing those two and learning how to, and this is always a challenge, and this is still very challenging as we're working on Converge version 5 right now, which hopefully will come out early to mid next year. It's like, well, what goes in Converge version 5? We have to balance what customers are asking for versus what we think they're going to want, right? And that's a balancing act that's pretty critical.
Yeah. I mean, I also want to give you the opportunity, Kelly, to a little bit pitch what Converge does, what it can do and what it cannot do. Like, who's the perfect customer using Converge compared to, let's say, all the other solutions that exist out there, SimScale, CFX, you name them. What is the main differentiator that you guys bring to the table?
Yeah, I think the main differentiator is we like to say we solve the hard problems. If you have something pretty simple like pipe flow, and I realize that's a really simple example, but if it's something pretty simple that can be meshed quickly, even using traditional approaches and other software, maybe we don't have a ton of advantages. I still think, I'm biased, I still think we do, because the way we do our AMR and the way we do our physical models and things like that, I still think we have an advantage, but we don't have as much of an advantage. Where we have a huge advantage, I think, is when you have a complex geometry with moving boundaries. Right? Or if you want to do something like fluid structure interaction, where the flow and the surface, right, interact. Conjugate heat transfer we're really good at. So anything that's a complicated problem, and usually what we'll do is, if we go into a new company, we don't say, give us your day-to-day kind of CFD simulation workflow or application. Give us a problem that you haven't been able to solve yet, or you struggle with solving. Right? And if we can show them that we can do that problem, that's a big win. And then that helps us kind of grow into doing the day-to-day stuff as well, because they see the advantage of using our code in general and they want to have a consistent workflow. So, where we really shine are complex geometries, moving boundaries. If you have reacting flows, the way we do our detailed chemistry solver and just the access we have to mechanisms and things like that, I think that's second to none. So any of those types of really hard problems, I think it's clear that again, I'm biased, but it's clear that we're better.
Yeah. How do you tackle challenges and innovations in CFD, especially when it goes to hard problems like, I don't know, multiphysics, thermal runaway, CHT, FSI that you mentioned? So you have the problem. How do you break it down in such a way that, okay, we have the Navier-Stokes equations. How do we embed this into code? How have you thought about this? Maybe you have kind of a mental model.
Wow, that's a really big question, actually. And that is going to depend on which of those things we're talking about, right? But yeah, you have this overall thing you want to do, fluid structure interaction, let's say, or CHT. And yeah, how do you go from not having it to having it, right? You don't just say, oh, go put a model in and come back in a week and it's done. I mean, there's a lot of interaction between so we have different solver teams. At Convergent Science, we have like a combustion development team, we have a turbulence development team, we have a multi-phase team, and we have an HPC team, and I'm probably going to leave something out, but we have these 4 or 5 different development groups, and oftentimes, especially with these multi-physics problems, it's not just, oh, you give it to one of those groups and they go off and do it, or one of those developers, they go off and do it. There's a lot of collaboration, because when you talk multi-physics, now you're touching lots of different pieces of the code. You're not just touching like this model or this subroutine. And so usually there's a planning phase where we get together and we meet and we bring in the key players and we do try to map it out. I would love to say that we have a strategy that's like plug and play, like this is how we do it. It's really case by case. But
Hmm.
what it really comes down to at the end of the day is the developers and our other engineers as well, because ultimately they're going to be running the software, working together to the common goal, right? So you have to, and this is what I tell people, like you can be the best developer in the world, but if you have the attitude that you're smarter than everyone else
Yeah.
and you know better than everyone else and you're not open to listening, that's going to hold you back in your career. But if you can be open to, discussing these problems with other people and having that healthy debate, maybe you're, arguing about how best to do it, I think that really helps. And I think that's how we get some of these big features into the code is we have just really smart people here that are willing to work together and toward that common goal. It's not about I want to be the one to put it in. It's that I want to help, and as a team, we need to get that feature in. And so that's typically how that works. Again, I wish I had a recipe, a cookbook for you. I'm still searching for that myself, to be honest.
Hmm. But I like the answer. Yeah. How do you deal with emerging technologies? We talk about obviously GPUs, AI, and machine learning in CFD. Do you see it more like Do you see it with a little bit of skepticism, or how do you already incorporate some of this secret sauce of AI into your development?
Uh, Both. I mean, there's definitely I think a healthy dose of skepticism there, and I think there needs to be.
Yeah.
And I think it sometimes or often I cringe when I see some of the stuff that's put out there. Um, AI is not going to solve the Navier-Stokes equations.
Hmm.
Now, AI can be very helpful in interpolating between conditions where maybe you have solved the Navier-Stokes equations. So don't get me wrong. I think there's a lot of use for AI, but I think we need to be intelligent how we roll it out. The way we're looking at it is we're doing quite a bit of work on the pre and post side of things. So when I say pre side of things, I mean like, can we use AI? And we haven't released this yet, but we'll soon be releasing um, essentially our copilot, a Converge copilot
Hmm.
that helps you install the software, helps answer questions about the software, eventually helps you set up a case, right? Or gives you input on how to set up a case. And then on the post side, how do we use AI or machine learning to help optimize a design? We've done a lot of that, where you have a big design space that you care about. You intelligently come up with a design of experiments, kind of set of runs to do in the CFD, and then you use machine learning to fit a model to that, right? A surrogate model
Yeah.
to that DOE, and then you optimize that surrogate model. So it can really save a lot of time in optimizing a design. So that's on the post side of things. Now, inside the code, I think there's room for AI as well. We're working on ways to use AI to help solve, like neural networks, to help solve detailed chemistry faster, and things like that, and maybe glean some information from, say, DNS data in order to help inform like a RAN simulation or something like that. Like there's definitely room for AI and machine learning and all of this sort of stuff within the solver as well. But I'm very much a skeptic when I see, just do this slider and then it's going to give you the answer. Well, what happens now? The really interesting stuff isn't the stuff I already know. It's the stuff outside of that box where I've trained it, and it's not going to work there, or if it probably won't work there. I mean, you see what I'm saying? So
Yeah.
I think AI is great, and we're definitely implementing it in a lot of ways at Convergent Science that you'll be seeing in the near future. But yeah, I have a healthy dose of skepticism there. GPUs, sort of a similar idea. For finite volume CFD, it's hard to beat CPUs on when it comes to performance and cost when you're looking at both,
Hmm.
right? And so, having said that, GPUs have come a long way, and some people already have GPUs in house, right? Because they have them for doing AI or something like this. So they want to be able to run their CFD on what they have, right? So we're making a lot of progress on GPUs and porting Converge GPUs. In the future, in the not so distant future, there will be a Converge version that fully runs on GPUs. So far, we've put out like chemistry solvers that run on GPUs and things like that. But in Converge 5, for example, you'll see at least part of the solver, the flow solver part, hopefully being running on GPUs. So we're definitely, again, there's some skepticism there, but at the same time, we do see a need for these things, and people want them, and I think over time they will evolve, and eventually it may be clear that GPUs are the way to go, even for finite volume CFD, even from a cost standpoint. We don't know where it's going to go. So we're addressing all of these things, but I do think it's important to not just jump on the hype cycle and ride that, to extremes. I think it's important to have some skepticism.
Absolutely. We mentioned now GPUs, AI, machine learning. What skills are you looking for in aspiring CFD engineers? Especially now, the people watching the podcast, there might be aspiring CFD engineers, maybe in the undergrad, whatever. They might be thinking, okay, I want to work for Convergent Science. Like, what is Kelly looking for in terms of, I don't know, character traits, motivation, skills, technical skills? Maybe you can give the audience a little bit of a hint there.
Yeah, no, that's a good question. Honestly, we're looking for sharp people who work well with others. And I know that sounds really cliche. It sounds like you're in second grade or something. Works well with others, satisfactory. But that's really important because sometimes, if one person brings drama to a team, I'll say, it can really bring down the morale of the whole team. And so I think, that's really important. So PhDs need to get over themselves. We hire mostly PhDs. Yes, they're brilliant people, but there's a lot they don't know yet. And just because they did something a certain way in graduate school doesn't mean that's how we do it in the real world, right? No offense. I mean, I'm a PhD as well. I went to graduate school, but and we're lucky. Most of the people we hire do really well in that, because when you interview people, you can kind of get a feel for some of that based on some of the questions you ask. If I say, what's your biggest weakness, and you tell me you don't have any, that's a red flag. I'm not going to hire you, right? Mm-hmm. And I've actually had that happen before. And so I think on the soft skill side of things, I think that's really important. I think I've talked about this before, but being a closer is really important. So in other words, you could be really awesome at putting in, let's say you're a developer and you come and work at Convergent Science. You could be really awesome at implementing a model, right? But sometimes the hardest stuff is testing the model, documenting the model, debugging the model, all of that. So being a closer and taking a new feature or a new model all the way to the end, seeing it all the way to the end. Sometimes developers, they want to just do the fun part, which is just, let's research how to do this and put in this model. Okay, that's cool. I got it to work for my one or two cases, but you know what I mean? You can't stop there, right? You have to validate it on real world cases, work with other people on the team to do that, and also work with our documentation team to write it up, because the theory probably better than anyone at that point. So that's another one. And then in terms of technical skills, I mean, just having good CFD fundamentals, I think is good. Having said that, though, we've hired people who didn't have a lot of CFD knowledge or didn't have, say, a lot of combustion knowledge, and they ended up on our combustion development team. And they just really can pick things up quickly, and they're really curious people, and they're motivated, right? So sometimes people are worried, well, I don't have this particular background, I'm not going to even apply. If it's something that you really want to do, I'd say go for it. Apply for it, because we ask a lot of questions that are not even CFD related. They're more like logic questions, right? Just to see how you think on your feet. And sometimes we have people that do really well on those, and we're like, you know what? We're going to take a chance on this person. They don't have a lot of CFD background, but they seem pretty sharp, and they seem pleasant to work with and things like that. Let's give this person a shot. Mm-hmm. So I guess I didn't really directly answer the question maybe, but I gave at least a lot of nuggets in there that I think listeners can take away, hopefully. And maybe I'll see some of you in an interview someday.
Yeah, definitely. That would be cool. Do you have any general advice or some things that you've learned over the last years for aspiring entrepreneurs? Maybe people who don't want to work in a classical 9-to-5, but they want to start their own company.
Yeah. One of the biggest pieces of advice there I would give is you have to be optimistic, sometimes unhealthy amount of optimism. I know that doesn't sound right, but you need to be, let me tell you a story. Okay, let me tell you a story where we did this. This was back in the early days of Convergent Science, probably around 2009. So in 2008 is when we released our software for the first time commercially, right? We were 4 guys. We had no idea what we were doing, but we did it, right? And that was actually a terrible time because the automotive industry was tanking at that time. Mm-hmm. But it turned out to be a great time because people wanted more efficient solutions, right? So it kind of worked in our favor. We did this really long benchmark and for a company and against other commercial codes. They pitted 4 or 5 of us against each other and said, we're going to pick a winner at the end of this. And they had all these different categories where they ranked us. Best solution, most knowledge on the topic, best support, whatever. So we scored the highest you could score on all of the categories except for one of them. And that one was the size of our company. Because I think at that time we were like 5 people.
Mm-hmm.
Okay, well, because they don't know, this is 5 guys, are they going to be around in a few years? Should we invest heavily into this technology? And so I actually was personally doing that benchmark. I did that whole benchmark. I spent about 9 months. I spent about a year on it, I would say. And they picked a different solution because of that one thing they were so worried about. And it was really tough for me. And I tell this story a lot because, I owe a lot to my partners, where one of my partners, Eric, he came in the room and he's like, yeah, I know this sucks, but I think we've got him right where we want him. I was like, what are you talking about? He's like, they'll be back. And in about 3 months or so, they came back and said, you know what? We made a mistake. We want to use your software. It was the right thing to do. We're willing to take the chance on we think you guys are going to grow, and it worked. And it's like having that sense of optimism, because there are going to be a lot of things that don't go your way, right? When you're trying to start up, it's the people that succeed are the ones that can kind of make it over all of those bumps, right? There are a lot of ups, there are a lot of highs and lows when you start up a company. And we've been through a lot of them as well. I could tell many, many stories. I won't bore you with them here, but being able to kind of see the big picture, see the finish line, see the goal, and okay, these things are going to happen. I mean, we got letters in the mail saying one of our customers was going bankrupt, and they may or may not pay us, and they ended up paying us, so we lucked out. But that was a big deal. We really needed the money at the time. So there are a lot of things like that happened over the years, and even now, everything. I mean, we're doing great, but there's still bumps. There's always bumps in the road. So for entrepreneurs, that resiliency, right? You have to have that. You have to have that optimism, and I think that goes a long way. And I said earlier, we were naive to think we could start a company in a new code. You have to be naive, right? Because otherwise, you're going to be like, what if this? What if that? Oh, that can't work. And if you keep asking yourselves those questions, you'll eventually stop, right? But if you have to have that, you have to be naive and you have to be optimistic.
Do you feel like, I like that. Thanks so much for sharing that. Do you feel like you have to be dumb enough to just fail as fast as possible? Because I feel like, especially people from academia, we have been trained to think in a very structured way. So I have to go from A to B, from B to C, whereas the dumb ones are the people who just want to fail fast and are pro implementation speed. It's like, I want to go from A to Z as fast as possible, no matter how much failures I have along the way. Were you that type of guy?
It's a combination of both. I mean, I do think that it's important to fail, and if you're going to fail, you should fail early. Yeah. And part of why it's important to fail is because you realize you can get over some of those bumps. Like I have this story that I talk about where, in the original version of Converge that we wrote, we were probably 18 months into it, a year and a half into it, and it looked pretty. The solutions looked really pretty. But it wasn't conserving, and we're like, this isn't going to work. This technique that we went down an immerse boundary route, which for what we needed, immerse boundary is great. It can work really well for some problems, but for what we needed, it just wasn't going to be robust enough and good enough. And so we basically scrapped 18 months of work. Now, I don't know if that's failing fast or not, but in the grand scheme of things, that's pretty fast. Right. Yeah. It's good that we pulled the plug at that point and said, you know what, we need to start over, instead of putting Band-Aids on it and keep going down that road because we didn't want to fail. We wanted to kind of make it work and get to Z or whatever. So I do think there's a good combination of both of those. I wouldn't suggest failing. You know what I mean? At some point you got to succeed, but failing early, I think you learn a lot from that. And I think it can really help you kind of see the big picture and kind of where you really need to go. And so I think for us, that was a really important thing to go through, is that failing after that 18 months.
Yeah. How important is motivation for you? Do you think motivation is a myth, or was there something that really motivated you and the team on a daily basis?
What motivated us?
Was it money? Was it to build something big?
Early on, it was the pure like because remember originally we were going to be open source,
Yeah,
and so originally it was just like we just want to give the world a better. I know it sounds I don't know cheesy, but we want to give the
altruistic.
world a better CFD solution, right?
Mm,
Of course, making money doesn't hurt. We need to survive.
yeah,
But early on, I mean, there were many months where we didn't make any money, and it was, again, it would have been easy to just give up and go work for somebody. But we stuck with it. And then eventually it got to the point where it's like, no, we want to be the biggest CFD company in the world because
I like that.
partly because we think we have the right foundation for that. Now, obviously, what's going on in the market is pretty crazy right now. Everybody's gobbling everybody up. But if you look at who's left in sort of the independent CFD companies, we are one of the biggest, if not the biggest, I would say, independent CFD company. Now, sometimes that works against us because customers want kind of an all-in-one solution, right? They want to write one check and get their finite element analysis, get their CFD, get everything,
Yeah.
right? Get their CAD, and some of these big conglomerates have that. But we still think, and when it comes to the CFD part, we're the best in class, and so that's usually what gets us to a purchase order.
I like that. I believe in you guys. So go
Thank
for
you.
it. Yeah, very cool. For the closing of the podcast, I want to ask you 10 fun questions. You can
Okay,
answer them. You cannot answer them. It's really up to you. But it's going to be fun, I think. So for the last 10 minutes, I'm going to ask you 10 questions.
sure.
Question number one. If CFD were a person, what kind of personality would it have? Would it be a perfectionist, an overthinker, or just someone who loves making grids?
I think it would be wow. I think it would be a very colorful person, very colorful personality.
Hmm.
And I think it wouldn't sweat the small stuff. I think it would be okay with 85%. This is a good enough solution. I don't have to be perfect all the time.
Got it. Cool. What's the most bizarre geometry or simulation request you've ever received? Did anyone ever want to CFD a teapot in a hurricane or something equally wild?
We did what did we do? A pig bladder or something like that? We did that not too long ago. That was kind of weird. What else have we done? I think we've done flow over a cow at some point. Everybody's done that, right? So we must have
Yeah,
been,
everybody. Yeah, it's like
especially being here in Wisconsin, we must have done that. And so, yeah, I mean, we've had some weird ones. We've done we've done like a curveball. We've simulated a pitch, a baseball
Yeah.
pitch, a curveball, and things like that. So yeah, there's been some weird ones along the way, but nothing too crazy, I would say.
Got it. Okay. If you could name a turbulence model after yourself, what would you call it? Bonus points for a catchy acronym.
Oh my gosh.
You don't need to get the bonus points. Just
The
how would you
Kelly
name
model, the K epsilon laminar
it?
logistical yippee.
Okay, I like that. I like that.
By the way, I did not see these questions ahead of time. I think that's apparent to the audience.
Yeah, but I like the answer. Question number 4. CFD engineers often joke about waiting for simulations to run. What's your favorite way to pass time while waiting for results?
It used to be playing music, right? I play guitar, I play drums, so I would often do that in the downtime. I don't do that quite as much as I used to, unfortunately. How do I pass time now? I listen to a lot of music. Honestly, the way I am now, I'm not running many simulations myself. I'm not running any simulations myself to be completely transparent. So there really is no downtime for me, unfortunately. I'm always doing something in Excel or making a PowerPoint presentation or something like that. All that boring stuff.
We're at that stage already. The Excel.
Yeah,
Time.
we're
Got
at that
it.
stage in the math.
Okay.
Yes, exactly.
Yeah,
I know
you
what
know
you're talking
the.
about.
Yeah,
Yep,
yeah.
yep.
Got
I'm at
it.
that stage.
Yeah, we have to share that with the audience if they don't know what we mean.
Yeah.
Okay. Question number 5. If you had to explain CFD to a 5-year-old, how would you do it?
Imagine solving, let's say, a 5-year-old. Um, Imagine designing a fluid device completely on the computer. And I think 5-year-olds right now are savvy enough with all the technology. I think they'd get that.
Good. Okay, I'll try it with a 5-year-old once the
Okay,
podcast goes live.
let me know how that works.
Yeah. If CFD were a sport, what would it look like? Competitive mesh generation races, heat transfer trivia? Question mark.
If CFD were a sport,
Yeah. How would it look like? Competitive mesh generation races, or how would it look like?
yeah, I think it would be competitive mesh generation, and I think we would definitely take the gold on that. Um, but I think the mesh generation would be the first part, and then once you're beyond that, it's like everybody wants the most accurate solution in the least amount of time, right? They want it to be extremely accurate, but they don't want to wait for it. So I think whoever gets closest in breaking sort of that trade-off curve, I think that's who would be the victor.
Mhm. What's your opinion on the age-old debate, structured versus unstructured meshing? And does it say something about someone's personality?
I think unstructured meshing. Of course, I'm a fan of Cartesian meshes, but I think unstructured is probably the way to go. Which our mesh is fundamentally unstructured. Yeah, I think people who want a structured mesh, I think they need to go to therapy a little bit.
Okay, so that's answered. If you had a magic wand that could instantly solve one CFD challenge forever, what would it be? And why is it convergence issues?
Wow. And why is it convergence issues?
Yes.
Okay, so no, we don't
But
have
any
any
problem,
convergence.
what would you solve? Let's say you could solve any problem.
That's a really good question. I think it's I don't know if this is appropriate for your question or not, but I think, you know, getting the runtime down to something where it's you don't feel it very much. The reason why I say that is because there are a lot of 1D and kind of 0D solvers out there that claim to be predictive and they run really quickly. And yes, they run really quickly, but they're not predictive. And so
Mhm.
I would love to just like wipe that off the list of arguments against CFD is like, well, it takes too long to run, right? So if we could somehow make it run, not even in real time, but something close, that's the problem I would try to solve.
Okay, got it. Question number 9. If CFD codes had theme songs, what song would be the best to represent Converge? Something like smooth and adaptive, like Rolling in the Deep, or fast-paced, like Eye of the Tiger? I think
Interesting.
Eye of the
So
Eye of the Tiger could match Converge. I feel. I don't know.
yeah, I like the song, and this goes along with my engine fascination as well. But I had to pick a walk-on song for a keynote I did a couple of years ago, and I picked "Fuel" by Metallica,
Okay.
and I think that fits nicely.
Nice. Good. I like that. And last but not least, what's the funniest or most unexpected thing someone's ever tried to simulate using CFD? Apart
I
from the
can't.
cow and hamburger.
I don't know if this is this a PG rated podcast or
Just say whatever you want. We're not gonna
no.
censor
No,
anything.
one thing we did, one thing one of our old partners did, who's now a professor. He won the Ig Nobel Prize for simulating a shower curtain. You know how the shower curtain kind of sucks in
Yeah,
when you're taking a shower. So he did that, and he won the Ig Nobel Prize for it. So I think that says a lot. I think that was one of the funniest things.
that's cool. I like that. That's
Yeah.
cool.
He
Good,
accepted
Kelly.
the award in a shower cap. So, Dave, if you're watching this, great job.
Nice one. Kelly, thank you so much. Any closing remarks for the audience listening to this podcast?
I think we've covered it. I think, if you're a CFD enthusiast, I think there's a lot of exciting stuff coming up in our field, a lot of really fun stuff. I would say don't get too enamored by the hype on some of these things, but kind of approach them with some healthy skepticism. And I think, CFD is going to be around for a long time. It's going to be used more and more. So you guys have a bright future, ahead of you if you're in the CFD world. And if you're in the combustion world, I think you have a bright future as well. I think, ICE and battery EVs, I think will be around. They'll coexist for many, many years, probably decades to come.
Yeah,
So thank
excellent.
you.
Thanks, Kelly. One last thing. How do you keep yourself up to date with the latest changes in CFD? Because there's so much going on. What are you doing? Visiting conferences? Like, what are you doing?
Yeah, conferences, reading websites, LinkedIn. I'm pretty active on LinkedIn. A lot of times you
I
see
like your
updates.
memes, by the way. I like your memes.
Oh, thank you. Thank you. Yeah, and obviously we have folks in our team where that's part of their job is to stay up to date. So yeah, a lot of conferences, a lot of webinars. Now a lot of things are virtual. It makes it easier to kind of get up to date on things. So that's how we do it.
Excellent, Kelly. Thank you so much for being on the show.
Sure. Thank you.